Hello, I wanted to share with you today some work that I recently finished for a master's in the Department of Philosophy at Carnegie Mellon University, and it involves homotopy type theory and identifying structures from differential geometry inside of there. So we bring into homotopy type theory in this work connections and curvature on bundles, also vector fields, and the index of a vector field. And we use all those elements to prove a theorem in 2 dimensions that the total curvature is equal to the total index. Now, where does that come from? That's part of this classical story where if we have a 2-dimensional smooth manifold without boundary and we add either of 2 different structures on top of that, either a connection on the tangent bundle with curvature f or a vector field with isolated zeros, then we can do either of these 2 computations in the upper left, the total curvature and the total index, and either of those is equal to the Euler characteristic. So what we're doing in this talk is bringing in the concept of curvature and the total curvature, the concept of vector field and index, and this total index, and we'll prove they're equal to each other, but we're not at this time figuring out how to bring in the Euler characteristic, so we'll miss that piece. So the classical story of vector fields and index is that near a zero of a vector field, a place where the vector field vanishes, there's only 3 possibilities, that there's an index of 0, +1, or -1. There are such things as higher index, but they can always be perturbed to split into nearby points that fall into one of these classes here. So the way you visualize what the index is you consider the winding number of the red vector as you move around the 0. So if you move around the 0, the vector's at 1 o'clock the whole time. So that's an index 0. Whereas here, the vector at the top starts at 12 o'clock and turns all the way around the clock face clockwise as you move clockwise. And that's true for these next 3 as well. They all actually rotate clockwise, even though at first glance, maybe you, like me, thought that one of these pictures should be index -1 intuitively. But in all cases, we just start at either 6 or 9 or 3 o'clock and wind around clockwise. And then to get a negative index, you have to do something like this, where you wind the opposite direction. So those are the cases that can happen. And the total index of a vector field, which is to visit all of the zeros of that global vector field and count up the index. And you obtain the Euler characteristic. That's the Poincaré-Hopf theorem. So for example, on this sphere, you could look at the vector field that points east, which has a 0 at the top and the bottom, and we just saw those. They're index 1. Same thing with this vector field that's like a height function or a Morse function on the sphere. There's a 0 at the top and the bottom, and both of those are instances of +1 index. So both of these vector fields are computing that total index of 2 that we know the sphere to have. So on the other hand, we had the Gauss-Bonnet theorem. Gauss-Bonnet theorem says that total curvature divided by 2 pi is also the Euler characteristic. And in the case of 2 dimensions, you could think of curvature just as a function, a real valued function. It varies from point to point on the manifold. So unlike the index, which is at these discrete finite number of points, this is something pointwise all over the manifold. And this integral just sums the value at every point, like an integral. So in the case of this torus, it has some places on it where the curvature is negative, and some where it's positive, and this ends up all canceling, and you get that global value of 0, total curvature, which is the Euler characteristic of a torus. So we're good there. And then in the case of a sphere, which just imagine it has constant curvature 1, you're just computing the area of the sphere, which is 4 pi. So it's important to divide by that 2 pi, and then you get 2. In terms of the homotopy type theory background, this is about the level that we will need here. The symmetry book, central H spaces paper, and Skokola's nilpotent types paper, which won't figure as prominently in this talk version, but in the formal paper version of this thesis, it's important for constructing examples of maps into Eilenberg-MacLane spaces. So here's our class of manifold objects. They are combinatorial manifolds. So the idea is we'll use the classical theory of simplicial complexes, including just them living in the type of sets, and we'll define a realization procedure in homotopy type theory to construct actual higher types out of those. So recall the classical definition of a simplicial complex. It's an ordered list of sets. There are n plus one of them for dimension n. The zeroth set is a collection of vertices, and then all of the other MKs are subsets of vertices. If you're in MK, then you have cardinality k plus 1. And it's downward closed. So if you're in MK, if F is a set in MK, and we have any subset, then it's in the appropriate MJ, depending on its cardinality. We can also truncate this ordered list at dimension k, and not all the way up to n. And that's called the k-skeleton. And we denote it like this with the less than or equal to. So an example on the upper right here, it would be just to emphasize the abstract nature as opposed to the pictures below. It's M0 in the case of the diagram in the upper right. I've got 6 elements. And then M1 consists of certain 2-element subsets, and M2 consists of certain 3-element subsets. And the edges I've drawn between them are not necessarily needed, since there's an entailment. If you read WBR in M2, then of course WB is a subset of that. The edges that I'm drawing here, though, are establishing or diagramming the poset relationship between these. And a diagram like this, you may find it out in the wild. It's called a Hasse diagram, and it's commonly used to denote like polytopes and shapes like that. This one, when you render it with a geometric realization, which is a classical set topological space idea, you get the octahedron you see below. And the name scheme for the W and Y and so on is coming from the faces of a Rubik's Cube, where it's like white on top, yellow on the bottom, blue, red, green, orange going around. And this will be our running example in this talk. Another example would be the complete simplex, denoted with this delta of n. So it's an n-dimensional simplex, but it's complete, meaning it consists of n plus 1 vertices, and then the power set of that, all of the sets. So this is like a ball, a contractible type space. The n-1 truncation, the n-1 skeleton of this simplex, we're going to give a special notation to with this boundary of delta of n. And that'll serve as our combinatorial n-1 sphere. So, for example, delta of 1 is 2 points and the power set of that. So it looks like this interval object. And its boundary is the 0 sphere, these 2 points, 0 and 1. So that's an example of how we're getting a sphere out of this. Delta of 2 is this ball that's this triangle filled in, and its one skeleton is the triangle not filled in, and that's boundary delta of 2. So we'll make use of these as we inductively build up the combinatorial manifolds in type theory. So the homotopy realization is the procedure we're going to define here. I hadn't seen this done elsewhere, but it's really just geometric realization, but performed with homotopy pushouts. We're going to work our way up by dimension, like I said, because in each dimension, we're going to sort of bank the sphere we need to, which forms then part of the definition of the next level up. So in dimension 0, we will just simply take the realization bold M, blackboard bold will be our notation for a type, of a 0-dimensional complex. M is just its set of vertices M0. So in particular, the 0 sphere, which will be written with this blackboard bold delta, is just the set of those 2 points in boundary of delta of 1. So boundary of delta of 1, or delta of 1 was the interval. Its boundary was a 0 sphere with 2 points, and that's all it is as a higher type as well. It's just a set. In dimension 1, we will use that sphere and we will form a pushout. So if we have a one-dimensional simplicial complex M, it's got the 2 sets M0 and M1, then the realization is given by this homotopy pushout, where the span we're pushing out is this combinatorial data that's telling us here are the edges, and here is a 0 sphere, and the map down here will encode which vertices this edge is supposed to connect to. Okay, standard way to form a pushout, and this is a projection. So we declare that we fill this in and form its pushout, which means that this M1 down here is made by declaring path objects, creating like a higher inductive type, generating paths between each pair of vertices that were connected in the complex. It comes equipped with this map down on the right here, which is M1 at the top is a set. So what this vertical map is doing is providing hubs. So each edge in M1 from these generating edges actually also has a hub, and then that's glued to the two endpoints through the push out. So the higher data here, the actual homotopy paths are provided by the filler here, and then it comes with these hubs. Now we're going to ignore these hubs. They may be useful for some applications, I'm not sure yet, but we're not going to be making use of them. So we'll just ignore them and just imagine the original vertices with direct paths between them. So now we need our sphere in this dimension, and then we'll go to dimension 2, and then we'll stop there for now. So the simplicial higher one sphere, so blackboard bold, is going to take this data of this triangle, and we'll actually build it with pushouts. So here it is symbolically with the notation we've been using for boundaries of these complete simplexes. But here it is written out, explicitly with the sets. We've got the 3 vertices of the triangle. Here's the 3 edges. And so maybe 0, 1 times 0 will go to the 0, one of the points in the vertex 0, 1, or one of the vertices in the edge 0, 1. And maybe 0, 1 times 1 will go to the 1. We don't have to do it in that order. This is a sort of an unordered construction, but that's one way to think of it. And then when we push that out, we'll get something that deserves to have a picture like this, but it's a 1 type now. Or we can form the one skeleton of our octahedron. So here are the 6 vertices are here. There's 12 edges listed here, and we push them all out, and we get something we can call bold O1, and it's this without the blue faces. Now in dimension 2, we'll make use of the 1 sphere to build ourselves up, and now, so this part of the push out, this push out is the one we saw, but now M is a 2-dimensional simplicial complex. So it has a set of faces, M2. So what we can do in this other push out, and note we have this sort of spine here. We have bold M0 mapping to bold M1, mapping to bold M2, because they form part of each other's push outs. So we obtain these maps. And I've just drawn the push out that takes us from M1 to M2 underneath to make room. Here are the faces indexing a set of triangles. And the map here into M1 will be the map that encodes the combinatorial data of the simplex. So for each face, this triangle will map to the triangle that face is bounding, and we'll do a push out. And again here, this map from non-bold M2 into M2 will give us a collection of hubs, if we want to make use of them, one for each face, a point for each face, which is then filled in with a homotopy to the entire bounding triangle. So for our octahedron, the full story would be this. Here's the 2 pushouts. So all we did is recapitulate. So here's one of the faces, white, green, red. So here it is in the picture, white, green, red. Now this picture over here is a reuse of our geometric realization, right, as a topological space. But I think we can still use it to drive our intuition about what we get out of this. We should get something that's equivalent to the 2 sphere in homotopy type theory. Last piece of terminology we'll need from the world of simplicial complexes is the link. This is a totally classical idea. The link of a vertex is the sets not containing W. Let me move myself here. There we go. The sets not containing W, but whose union with W is a face. Now that language is meant to just give you the faces that are nearby to W, so that when you union any one of those faces with W, you get another face. So in the case of a 2 complex, you'll get this ring, this circle, polygon, that are the neighbors of the vertex in question, the neighbors of W, and the edges joining them to each other. Because after all, the edge GR, if you union it with W, you get this face. So that's how that language works. And classically, again classical from the 20th century, a combinatorial manifold is a simplicial complex, all of whose links are simplicial spheres, like this one, like the octahedron. They're all simplicial circles, polygons. And when I say R, it means the geometric realization is homeomorphic to a sphere. That's the fine print there. So this will form our model of the tangent space, in addition to restricting our class of objects. So we restrict class of objects so that they have a link. Every vertex has a link, and that will be our model of its tangent space. So instead of being an infinitesimal object at that vertex, it's a finitary object of neighbors around that surface. Let me move myself back here. Okie doke. So this justification for why this is a reasonable class of objects to consider comes from this big theorem from 1940, which is that every smooth n manifold, all dimensions, has a compatible structure of a combinatorial manifold, which we just defined, a simplicial complex of dimension n such that the link is a combinatorial n-1 sphere. And you can read more about that at this NLab page if you would like. So basically what we're dealing with here at least includes finitary, discrete, combinatorial representations of smooth manifolds. So what's a not combinatorial manifold? Well, here's something that, according to Wikipedia, is a simplicial complex. It meets the definition, but of course it has this dimensionality problem. It's got some two cells, but it's got some one cell sticking out. It's not coherently a two-dimensional thing. So obviously that will fail the link condition, because some of these points on like this arm, this one, the link, the two neighbors, they're not connected to each other, so it fails. I don't know what all else can go wrong. Maybe there's something where it looks at first glance like a two-dimensional surface, but there's something technically going wrong with the links. I'm not quite sure. So where will we be mapping these objects? Well, we want families of torsors. Those are what are also called principal bundles. So we're going to look at spaces of torsors. What is a torsor? If G is a group, including the case where G is a higher group, like say S1, that'll be a fundamental use case for us. Then first of all, we have the idea of an object being acted on by G. A right G object is just some type and a homomorphism from the opposite of G to the automorphisms of X. And it's the opposite because we're acting on the right. And then, so if you're a G object, you might be a G torsor. You are, in fact, furthermore, a G torsor if X is inhabited and if the following map is an equivalence. So this map is a packaging of X times a copy of G to X times X. So the second coordinate of that map is the group action, phi. So in other words, X times G to X is just the group action. And we add the projection as well. And this packages together some of our fun intuition, like that X is almost a copy of G once you pick a base point. We can give a name to the inverse of this function, though. So we said it's an equivalence. If we call the inverse first projection and a function S, then that S is a map from X times X to G, which we can call subtraction, which is an intuitive good name if G is commutative, which it will be in our case. But in other words, it takes 2 points in X and tells you the unique element from G that sends one of them to the other. The type of these we call BG. That's a common notation because it has G in the name, and we think of it as a de-looping of G. So speaking of which, if we pick a base point in this space BG, this universe of torsors, then we can have the special case of the torsor of G acting on itself on the right, and we can call that G reg regular. Not meant to be my name. I didn't pick this notation. Then we have some facts such that the loop space of this type of torsors, BG, at that base point is equivalent to G itself. So we've de-looped G. And in this loop space, composition of loops corresponds to multiplication in G. So that loop, that loop group is G. We've de-looped G. BG is also connected, and therefore 1 and 2 together prove that BG is a KG1, an Eilenberg-MacLane space for G. The H spaces paper has a lot more about these constructions. So how are we going to map into the type of circle torsors, S1 torsors? One way to construct it is to think about lifting a family of mere circles, because we have a sequence like this where BS1 maps to B_S1, which is a connected component of the universe. So B_, is a hopefully standard notation for the connected component of types merely equal to that one. So the pairs of Y a type and a proof of inhabitation that Y is equivalent to the circle. So those we can call mere circles, B_S1. So we can start there and have a family of circles and then think about or prove theorems about what it takes to lift that or prove that it factors through BS1. And we'll just assume during the talk here that we have such a lift when we need it. And in fact, in 2 dimensions, where the link is circles, it corresponds to a choice of orientation. Or in general, if we're mapping to some other family of mere circles that isn't meant to be the tangent bundle, some other family, again, that bundle can be oriented, and then it'll lift. So some other names for some of these objects that may or may not help you understand what's going on here. B_S1, which is the automorphism to the circle, can also be thought of as BO2, where O2 is transformations of the plane, like rotations and the flip. So just like B_S1 includes some kind of rotations of S1, but also the flip that reverses the direction. It can also be called EMZ1, and that's what I call it in the companion paper to this talk, because that's the Skokola notation, the paper I mentioned earlier, where this EMZ1 is meant to be the type of Eilenberg-MacLane, mere Eilenberg-MacLane spaces. The thing, types merely equivalent to KGN, and that's called EMGN. Meanwhile, BS1 we could think of as BSO2. So there's where we've removed the flip from O2 and we just have rotations, which is, of course, a copy of the circle. And that's the point, is that a torsor is a copy of the group. And that's also KZ2. It's a de-looping. The de-looping of S1 is a de-looping of a KZ1, and it's a KZ2. So as I promised, we're going to be able to just see in what we've defined so far maps into these types of torsors. We're supposed to observe, we will be observing in there that connections and curvature are there. And that will just emerge from the fact that we have this simplicial complex structure, dimension-wise structure to deal with. So simply put, connections are extensions of a bundle to higher skeleta. So we have some kind of definition inductively up to some skeleton, and if we extend it, that deserves to be called a connection, and we'll see why. So for example, the link of the vertex W in this 2 complex, which we talked about, right? The sets not containing W but whose union with W is a face, is a polygon associated to W. And so we can define the tangent bundle on a combinatorial manifold to just be the link. Now this is defined only so far on vertices, on the 0 skeleton. So we'll call it, instead of just calling it link, we'll call it T0, because we're going to build up and extend it to the higher skeleta and see where connections come in. So like I said, a connection is an extension. So an extension of T0 called T1 to the 1 skeleton of M, which is M1, we'll call a connection on the tangent bundle. So M0 maps to mere circles. We call that T0. And if we extend it to M1 so that this is commutative, then we're calling that a connection on the tangent bundle. So what's that look like? So let's use the octahedron, and we will extend link to edges. So let's start by just defining T1, the extension of link, on one edge, WB. If we want to define T1 on an edge, we need a term, we need a path between link of W and link of B. Right? T0 maps W to link of W, B to link of B, and we need an isomorphism between those two. These 2 squares. We can do that by visualizing tipping the equator square into this vertical line of longitude square. Now, we have a choice here. This is a choice we're making. This tipping concept is our way of saying this is intuitive. We're leveraging the fact that we're thinking of this as a picture embedded in three-dimensional space, and we're going to map. We're going to use this as a rule, but we actually have to write down all the data. So below we see if you were to start to write down all the data, we would define T1 on this edge needs to map that whole square, GOBR, to this one. So what does this T1 of WB edge do to G? It maps it to W. So it takes G in the link of W. Here's the link of W. It takes G there to W at the top of the link of B. Okay, and so on. You can see that it will take O to O, R to R, and then it'll take B in the link of W to Y in the link of B. And then we can use this same method, this tipping visualization, to do this for all the edges. It's pretty intuitive. And in fact, catch this. Let's look at T1 on a whole closed path. Okay, we're going to build up to T2, right, where we want to extend it to the face. But let's just think about still paths. So think about concatenating WB with BR with RW and going around this loop so that we should get an automorphism of TW in so doing. So let's denote this path by boundary WBR, where WBR is meant to represent this face, and here's its boundary. It happens to be pointed at W. So we want to define T1 on that. Well, we already defined T1 on all the edges, so we're going to compute T1 on this from what we know, which is that it tips it up. On its way from W to B, it tips to here. On the way from B to R, it will turn to sort of face us here. And then, by the way, the red edge is just here to help us sort of see what's going on, to identify the one of the edges, to follow it as it moves. And then finally, it sort of tips itself backwards like this. So we observe here, we've come back, rotated by a quarter turn. So this is a discrete capturing of non-trivial holonomy around a loop. We've tipped up, around, and down, and so some geometry has taken place. This polygon has rotated. We'll name that quarter turn rotation R, and it's an automorphism now of link of W. In fact, it lives in BS1 because it is an orientation-preserving rotation, but we're punting, worrying too much about the distinction and when our maps lift in this talk. Now that we've looked at the loop, we can look at the face. So if we were to extend T1 to this one face, WBR, then we would need to think like the following. First of all, the face is a filler of some kind, right? It's a path, a two-path, from Refl W to the loop. Let's give that the name HWBR, H for homotopy. So it's a two-path that fills this in. So therefore, T2, if it's to extend T1, then it has to be like a natural transformation. It has to take us from T1 of this point to T1 of that. T1 of this path to T1 of that path. T1 of this path is the identity, and T1 of this path, loop, is R. Right? So T2 would have to be a homotopy, let's call it H big R, from the identity to R. So that will be a homotopy between identity and rotation. So it's a path in the automorphisms of link of W. Well, that's pretty easy to construct. Again, though, we have some freedom here. We're going to pick the minimal thing so that what this homotopy does to, say, the point G, I need to provide a path from identity of G to R of G. So identity of G is G, R of G is O. I will choose the edge GO to do that. So there's not that much difference between big R and H sub R. To me, at least, I get confused. R is this rotation, and HR is just sort of intuitively the connection to the identity, the path from the identity. So it's like having a movie of R being performed, and we're going to choose the one that where R is the landing place. We're going to choose the minimal clockwise one that implements it, the path from identity to there. The original inspiration for, in fact, this whole project was, you think about the Rubik's Cube, which is the dual of the octahedron, right? So instead of a white vertex, we have a white face on top, and we have, instead of 4 vertices around the equator, we have 4 faces. But it's a dual because they're barely different. The face moves to the blue face, sliding in the most sort of parsimonious way possible, bloop, and then it goes from blue to red just by sliding and then back up, and yet it comes back rotated by 90 degrees clockwise. And if you imagine when that happened, it happened here as it moved from the blue to the red face, because white to blue and white to red or red to white really don't do much. But with respect to white, imagining being based at white, moving from blue to red is a rotation. So that's where it kind of happened. That's just how I think of it. So the formal definition of a connection for any dimension is that if we have a realization, like we defined this higher realization, of a combinatorial manifold of dimension n, and here I've named the sort of what we were calling the spine of the maps that map the skeleta, between the skeleta. So if M is a realization, here it is all spelled out here in skeleta, and all the triangles commute in this diagram. So we've got a type family that keeps, that it's we can extend F0 to F1, or we have extended it, and so on, meaning these all commute. Then we can give some names to this and identify some classical stuff. So we can call Fk a K bundle on M. So it's just on the K skeleton. And we can call the pair given by the map Fk and the proof that there's a commutative triangle with Fk minus 1, i.e. that Fk extends Fk minus 1, then we call that map Fk and that proof a K connection on the K minus 1 bundle. So it's like I said, so a K connection is just an extension to the K skeleton of something, a type family defined on the K minus 1 skeleton. So we have enough data around to also talk about curvature. So now let's get down to the individual push-out level where we have, say, a face, some faces here, and we're claiming that T1 extends to T2. So that's our 2 connection that we claim exists. The data of this is an extension to T2, an extension T2 of T1 on each face. So let's just pick one face that's in this non-bold M2, and let's look at the outer square, and that's what I've drawn on the right, the outer square, single face. So this is declaring something like that at this hub point, right, that the T1 on the hub point, there's a filler to T1 on the triangle. So the filling of that face, like we just defined for the octahedron. We can call T1 of the triangular boundary of the face, we can call that holonomy the curvature at the face F. So if you, like me, are often confused between holonomy and curvature, holonomy is defined in more generality. It's on arbitrary paths, okay? But something about curvature is very local. So for us, it's defined only at one face. So holonomy, while more general, can be also computed just around a face locally. That's called the curvature. And then this filler of this diagram, which is a proof that that curvature is trivial, is called a flatness structure for the face. So we have something rather liminal here. We do have a proof of flatness of this, a proof of no geometry. But we also have our hands through all of this inductive structure of this simplicial complex and all these push-outs. If we remember all that data, then we actually have access to a specific proof that flatness is true on this face. So we kind of know that there's a non-trivial holonomy, but we have a path to the identity. So for someone like me who's been struggling for a long time to find curvature in a homotopical setting, this is one way to square that circle, so to speak. Yeah, the distinction between the path and its endpoint, it's like I was saying with R and HR, is small enough to be confusing to me. So if you're confused, you can join the club. Let us now talk about vector fields, the last piece of new construction that we'll need. Okay, so the setup is like we had before. Let's say we have T, an extension of link. So it's very important for vector fields that they're defined on the tangent bundle. So this is T is an oriented tangent bundle. So now we're declaring that we have that lift from mere circles to S1 torsors on a two-dimensional realization of a combinatorial manifold. So we are not doing vector fields in general dimension here, just two. Right? Well, note the following. This seemed like a problem. Our bundles of mere circles can only model non-zero tangent vectors, right? So our model of the tangent space is those neighbors and the circular, the polygon that joins them together. So we don't have a zero vector analog in that. So a global section of this family, in other words, a global section, a global non-vanishing vector field, would be a trivialization of T. It's literally, like you see on the right, a lift to ES1, to the point. So that's not a good definition of a vector field, because we literally can't have that a lot of the time. So this was a conundrum. So the solution that is in our paper here is that a vector field is a section, but only on the one skeleton. So we cannot extend it to all the faces. That would be a complete trivialization of the bundle. So a vector field is a non-vanishing vector field on, thinking classically, it's a non-vanishing vector field, but only on the one skeleton. So the fact that a general vector field classically has vanishing, we have modeled by omitting faces. So in other words, it's like saying that classically we're going to assume, in order to get into this picture, that let's say we started with a classical manifold and a vector field on it, we're going to have to push the zeros into the faces. So let's say we have a sphere and we're going to triangulate it into an octahedron like this. We're going to have to move the zeros into faces. And in fact, the punchline of a lot of this is that if you go reread some of your classical proofs, like in a book by Tristan Needham I'm going to cite later, that's literally how they go. They say, let's triangulate the manifold, and then let's assume we did that so that the edges of all our triangles and the vertices miss the zeros so that they're on the interior. So we're going to just take that seriously. Now I've drawn a sample vector field here, and we're going to use this as our example on the octahedron to compute total index and whatnot. I've drawn it a little deceptively because I've drawn arrows on the manifold, but of course the vector at, say, W is a choice of one of its neighbors in its link. So, right, it's a section, so it's a choice of a point in the link for each. And I've gone ahead and drawn it as an arrow from W to R because intuitively R is in the link of W, not in a bundle, but it is literally because it's its neighbor on the manifold. So I go ahead and draw it as a path to its neighbor in the manifold. I hope that makes sense. So this particular vector field, which swirls around the WRG face and it swirls around the YOB face, is given by, or in fact extends to, a full movement in 3 space of this. If you have like a D8 dice, you can turn it in this way. You can move it in space. So this vector field extends to an automorphism of the whole octahedron in space, spatially. So that's why this one, I don't know that there's very many that can be pictured like that, but here's one. Just a quick reminder then, right? So we have now sections of our bundle, and so we're going to look at what those do to paths. So we're going to talk about pathovers. So let's recall here quickly some stuff about pathovers, dependent paths. And recall that there's an asymmetry in their definition, right? So if we have a type M along the bottom here and a path in it from A to B, and here's a type family above it, and let's call that, let's say that type family is, the total space of that is called P, then given a point alpha over A and a point beta over B, the type of pathovers that lie over P are the type of paths from the transport of alpha, transport using P, to beta. Okay, so we sometimes get to blur that and think of it as a path directly from alpha to beta. But since alpha and beta live in different types, and so this is a heterogeneous type family, right? We don't have paths like that. Homotopy type theory doesn't have paths between points in two different types. But we can transport alpha to the same fiber that beta is in and look at the paths there. That's the asymmetry. So we have to use like a lens of transport through P, either from alpha to beta or beta to alpha, or B's fiber to A's fiber, or A's fiber to B's fiber, and look at paths in one fiber, so make a choice. So the last point here is that dependent functions, which are maps up, right? So they're sections from M up into the total space P. They map paths to pathovers. They choose. They provide a choice of a pathover for each path. So we call that APD, dependent action on paths. So APD, if we had X, a section, a vector field of a path P, then that would be a particular term in this type. Transport X of A equals X of B. So X of A would be our alpha, and X of B would be the beta in this picture. And we can just call that X of P, like what X does, like AP, regular action on paths. So our next goal is to define the index of a vector field on a face by computing X of the boundary path. That's what we're going to do. We'll use some pictures here. So I think I might have to move again. Let us do that. I'll move over here. Good. So here's an example face. It's got the vertices V1, V2, V3, and then there's the three tangent spaces, the three links, T1, T2, T3. And I've named the edges EIJ. And we'll look at an example of what we're going to call swirling and then index on this face. So here is a representation in gray, these outlined squares of the three links, the three tangent spaces at each of these three vertices. And we'll denote the value of the vector field X at the first vertex V1 with that thick black arrow there. Okay, and we'll call it X1. So we'll give it a nickname. Instead of saying X of V1 all the time, we'll just say X1. So X1 is a term in T1. Now, in order to do the path over thing, we're going to want to transport it around these edges, this one vector, because we're going to need to pick a single fiber to do our computation of X of the full cycle. And we will pick this T1 to do that. But we're going to need to transport X1 all the way around the triangle, among other data. But let's just think about this part of the data first. So let's say T21, which I'm using the notation T21, is a little backwards, but it's meant to be function notation. So T21 is the transport along edge E12. So T21 takes terms in T1 and turns them into terms in T2. So if we think of them as input, they eat terms on the right and spit out on the left, then T21 kind of is meant to show that things move right to left. Anyway, let's say that T21 from this corner of the triangle to the top is trivial on our screen here, so that it's just a rigid rotation. And then we will draw the transported vector as a little bit thinner so that we see that this isn't the value of X here. This is the transport of X from somewhere else. So let's say then that T32, right, goes again from T2 to T3, that it rotates clockwise by 1/4 turn. So now I've drawn it as dashed to show that it's a little more faded out. It's been transported twice by the time it got here. That's what the thinness and then dashedness is supposed to show. And then it turned to the, 4:30 position on the clock. Okay. Finally, let's say that T13 along the bottom, the blue edge, is trivial again. So it just slides over. So that dashed arrow slides from right to left to become dotted. So this is our representation of this very same thick black vector after it's been transported around the whole triangle. Comes back like this. Now that's just part of X of the loop, right? That's X of V1 then transported around. But there's X at other vertices, and then we want to look at X on the edges. So in order to do X on, say, E12, we need two more pieces of data. We need to finally choose a value of X at T2, and then we need to choose a path between the transport of x from v1 and that. So that looks like this. So let's say that we've now got x at v2 is this thick one. Here's the thin one we had transported from v1, and it is on us to pick path over style, a path from the transported one to the x, the native one. So that's this. We're coloring it the same color as the edge that put it there. So in a way, we're taking this path in the manifold, and we're looking at paths in a fiber that it generated. Okay. Now, meanwhile, so moving to v2, we had to introduce two new pieces of data, the x and the path. When we move to v3, all of these three pieces of data, these two black vectors in the red, will turn 90 degrees. So here they are, and their vectors got thinner, and the red is now here. But it's sort of rigid, right? It's still one clockwise notch from here to there. But then now, of course, we've got x at v3. We'll choose this corner of the square, and then the cyan greenish edge of the triangle appears in this way. So again, transport of this black thick one, which is this thin one. We need a path from there to the thick. So there it is. And then that picture, which is now 3 points, 2 edges, 3 vectors, gets transported trivially over to here, meaning no more rotation. So here's the cyan and the red still, and here's those 3 vectors. Here's our original vector. And again, in order to define the path over E31, we need a path from x of the transport of the most recent thick guy to the new, to the x of native to this fiber. So that's this blue line. All right. So all in all, we've visited every edge of the triangle and pushed all of the data we encountered along the way to this final fiber. And we've got this 3-sided thing because this was a triangle. But it's a 3-sided thing in a square, so that's kind of funny. It's a square because it's like the octahedron has square links. So it didn't close. It isn't a closed shape. And, of course, the gap between where it ended and where it started is due to the fact that there was a non-trivial holonomy around here because there was a rotation by 90 degrees. Okay? So we translated all the path over data to the end of the loop. And to me, it just vividly made me think of scooping the ice cream from the triangle. So I moved an ice cream scoop, and it moved the ice cream from lying across the top of the ice cream container to being vertical in my ice cream scoop. And by the end, I've got this tall, Neapolitan ice cream in this fiber vertically now. So the total path over this path, red catted with green, catted with blue, is called the swirling of x at the face f. We'll call it xf. It's really just x of the boundary, right? That's called swirling. And we need this intermediate concept for a couple of reasons, including our big proof. So that's why we're defining that. Here's that story we just told, but sort of symbolically, where I have the fibers T1, T2, T3, back to T1. And as I moved along the triangle, I added more and more data. So each time I added a new value for the vector and a path over. So that by the end, we've got 3 additional vertices, so 4, and 3 paths. Okay, let me, I think I can move myself back. So here's what we've defined so far. We've got transport around a face. We can call that TRF. And we called that curvature. Then we've got the flatness structure on the face, which is a path from the identity to the thing above, right? To the holonomy, to the curvature. And then we've got swirling, which is X of the boundary path around the face. And that's a path from the transport around the face of X1 to X1. So notice the relationship between these two. If you were to plug X1 into flatness, you'd get a path from X1 to transport of X1. And this is a path from transport of X1 to X1. So these two can be catted to make a loop. So that's what we'll call the flattened swirling. So the flattened swirling of the vector field on the face is this loop. LXF. So it is the concatenation of flatness of x1 with xf. And that's a path from x1 to itself. So what's up with that? So how does that appear in our example that we worked through? We had, remember, the red, the cyan, and the blue. And so now we've got a path that starts at x1 and goes to its transport, which is lovely because then the transport came around like this back to x1. So that's what the flattened swirling is. It's a loop, so that's why it's an L, and it starts and ends at x1. And the index will be the winding number of that. Very similar to the classical definition. It's the integer such that, right? So if you're happy with that, if you're intuitively like, I see what winding number is in this square, then you're good. But you know, if you want some fine print, we're going to only really be able to do integers as the loop space of the circle, S1 itself. So we need to map this square to that circle. So I've just written some fine print that is the integer such that in the circle has, of course, base and loop. Loop is its path. Loop to that integer is this loop. And this whole minus x1 business we will dwell on much more, but that's because we can recall that T1, or this fiber, being an S1 torsor means that we can use subtraction to obtain an equivalence with S1. Remember that? We can take 2 points and say, what's the unique S1 that maps one to the other? Well, not only do we have that torsor structure, we have a point. We have X1 in the fiber. So we can say, what is the, given any other point in T1, what's the unique S1 group element that maps that to X1? So now we have an isomorphism between T1 and S1, and that's where we can define the index to be a literal integer. But if, like me, you're happy to think about things swirling once around the square, then this is just a preview of this subtraction isomorphism that we're going to get to for our proof. Okay, so we have all these ingredients: curvature, flatness, swirling, and flattened swirling. So now we're ready to state and prove the main theorem. So we can think of this as a procedure of simplifying swirling. Swirling involves concatenating dependent paths. They're dependent paths. So we had to be very careful about lining them up head to tail in one fiber by transporting them there together. Can we simplify that? Can we stop doing that? So we got to pay off all our assumptions we've made. So for example, the torsor structure and the vector field. Like I said, we can use subtraction. Okay, so here is the final column from our symbolic representation of our example around the triangle. Right, where we had x1, and then we transported x3 to x1, and then we transported x2 to 3 and then 1, and we transported x1 around the whole loop. And then these are the three paths we got. We can define now for each fiber, Ti, an isomorphism with S1, because we have a torsor structure and a point. X gave us a point. So subtraction of whatever, taking whatever minus xi is an isomorphism between Ti and S1. It's like saying we trivialize the bundle on the zero skeleton. All the fibers have a given isomorphism with S1. And we're using the torsor structure and the vector field. So now that we have that alpha I, that equivalence, we can start to push different things we've defined, all of our structures, into just S1. We're going to remove the dependency in that way. So for example, rho ji will be what tji does, but now looked at in S1. It's the rotation that tji performs. So you can think of it with this commutative diagram. You've got tji, which we defined a while back. Each of these fibers is equivalent to S1, each with their own private alpha I, alpha j, such that whatever the map from Ti to Tj does, we can ask what it does in S1 like this by going around the other three edges, and that'll be adding the angle rho ji. It's a rotation. So intuitively, we know this, that transport around in our two manifold is just going to perform some kind of rotation. Now there's maps up too, right? We can take the base point in S1 and map it to xi. That's the inverse of alpha I. Same thing over here. A lemma here is that the angle we obtain from looking at what Tij does is opposite to the angle when we look at what Tji does. And that may be intuitively quite obvious, but just to spell it out, here it is spelled out sort of algebraically, but let's look also at the diagram. So Tji goes this direction, and Tij, right, the definition of Tij is that it is transport along the edge that goes from I to j. That is the inverse edge to edge from j to I. Eji, Eij, those edges from our simplicial complex. So those two are inverses. So the fact that going from Tj to Ti is the inverse of this map, that's the identity. But to do it down here, to go down and over and up first, that must also be the identity. Therefore, the angle that we get going from right to left must be the opposite of this angle. That's how to look at it. Continued. So we've now pushed the fibers to S1. We've pushed transport as angles in S1. And now we're going to push the path overs as paths in S1. So we're going to call sigma with the same indices as x. So xji is the path over, right? Like these ones, x13, x32, x21. We can now subtract xj from that. That's just our isomorphism of the fiber that this is in to, so this is now going to be a path in S1. And in fact, it's a path to base, because remember, it's a path to x natively in that fiber. That's the one that we're subtracting by. So that's base. And then this is the rotation of x from a neighboring fiber into this fiber. And we just gave that a name. It's the angle, rho ji. So sigma ji is a path from rho ji to base. So now somehow we've taken all the edges in the manifold and we've decoupled them and we've mapped them all, and we have this sort of family of a whole bunch of paths ending at base, living in S1. So paths of that form, something equals base, these can be directly added. This is the dependency now truly eliminated. How do you add two things that end in base in a group S1? It's a general thing you can do with a group. We have a plus operation from a path like this and a path like this to a path from A plus B. Now these are terms in S1. We already knew how to add them to base. And the way you do that is you just do what we were doing in the type family, is we shift one of the paths in A equals base, so that P is a path from A to base, by B. We just add B to it, which is like a whiskering type of operation. This is now a path from A plus B to B. And then Q is a path from B to base by assumption, so we cat them together. So that's how we get a path from A plus B to base. So it's so similar to that path over idea. Well, let's transport it to some fiber. That's what plus B is, and then add them there. So that's what we've done. And now we have another lemma about the invertibility of this, so that passing over edge from I to j or the edge from j to I, the sigmas give us paths that cat to REFL. So this plus operation is our new one, right? So sigma ij is a path from something to base. Sigma ji is a path from something else to base. And when we add them together, it's not even clear a priori that we should get something from base equals base. But we know that it is because the rows cancel. So here's the full proof. We know that APD, dependent action on paths of REFL, has to be REFL. That's how the path induction gets started. And that's the same as this statement, that getting xji into the same fiber with xij, which is done with transport, and catting them is REFL. And that's the same as saying now, if we use alpha to map the x's to the sigmas, then we get REFL. In other words, because Tij, right, this operator here, is just translating xji so as to be cattable head to tail with x. This should say ij. Okay, so it's just unraveling that definition and saying they cats to ruffle. So like this. So for example, I don't know if this picture helps. It's a little busy, but let's say that here's our path P, and we're talking about traversing P and then P inverse, and the fact that we get ruffle up here by doing X on that, right? Moving from left to right, we get a picture like this in this fiber of X of P. It goes from transport XA to XB. And then we can get two different paths on the left here. Either we can start over in this fiber and transport through P inverse, and that's what this downward one is. No, sorry, it's what this upward one is. Or we can take the one we built over here and transport it back, which is this downward one. Okay, and the point is those cat to ruffle. So now there's more assumptions that we can pay off. That was the main gist of what's going on. That was peak complexity for this talk. Now we want to cash in that our manifold has no boundary and that S1 is commutative. So if we enumerate the faces of M, F1 through Fn, and if we designate a base vertex for each face's boundary, so we pick a VI for each Fi, then all of the loops around each face, boundary Fi, right? They're all loops now. They're paths from VI to VI. Let those be all the triangular boundaries. We can now define the total swirling. So now we're starting to total things up. Up to now, everything was just in one face. Now we're totaling all the faces. To be the swirling with sigmas like we just defined, right? We have to map them now to S1. So this is an equation in S1 of a bunch of paths added together. Total swirling. We'll call that X-tot. We're going to assume that this expression involves every edge once in each direction. That's a two-manifold with no boundary. And if we started with a simplicial complex that used simplicial complexy language to declare itself to have no boundary or something like this, then probably we wouldn't have to make a fresh copy of that assumption here. We would prove this. But we're not too worried about it. The fact is that we will traverse each edge once in each direction. And because we just proved that each of those sigma delta Fi's, right, which is a concatenation of three sigma on three edges, because we proved cancellation, this completely cancels this X-tot. X-tot is just ruffle, ruffle of base. S1 is commutative. So remember all our constructions on one face. We've got the curvature, they got the flatness, we've got the swirling and the flattened swirling. Then we can total all of them in S1. We can get the total transport, which is the sum of all the angles across all the edges. And that's just the base point of S1. That's 0 in our group, because all those rows cancel. And then in the upper right, we've got X-tot, which is the total swirling, which we just proved also. All the sigma ij's cancel with sigma ji's. So those paths all cancel, and we get ruffle base. And then we have the total flatness and the total flattened swirling. The total flattened swirling, which remember the flattened swirling is the flatness structure plus the swirling. So it's a sum over faces of the flatness plus the swirling. Everything's commutative, so we can reorganize and sum over the sigmas, which we know cancel. And what remains is the sum of the flatnesses. So there we see it, the bottom left, bottom right, that the total flatness structure is the total flattened swirling. So that's it. That's how we say it in our lingo. The total flatness equals the total flattened swirling. And that's our main result. So on the octahedron, remember back that we had this capital R and the homotopy that goes from identity to R. So each face contributes an exactly identical copy of HR. And that HR is a path that's a quarter rotation. It goes from the identity to quarter rotation. So when we sum up 8 copies of a quarter rotation, we get 2 rotations. So there's the 2 Euler characteristic in terms of total curvature. Meanwhile, this example we showed of the swirling was in fact the what we were computing earlier with our large triangle and went around it and got a one winding number around the square was exactly the journey around this face, and we get a similar result going around this face. So the total index, you get a +1 from the WRG face, a +1 from the YBO face, and a +0 from all the other faces. So we get 2 copies of +1 for another total of 2. And then, like I was mentioning, the classical arguments, if you look at this picture, this is straight from a recent textbook on differential geometry. He's proving the equality of Gauss-Bonnet, Poincaré-Hopf, the equality of total curvature with total index. But he has to triangulate the manifold and have the 0 fall inside of the face. And then there's this, we don't have to get too much into this, but this capital phi, which is the notation that Hopf used in mid-20th century to make this argument, is the angle, the change in angle from the vector field and a parallel transported vector along the edge. So we have like a vector field that varies along the edge and transport along the edge. And the change in angle between those two is this function on the edge. And to me, that looked a whole lot like path over, which is like, hey, do the transport and subtract from what was natively there. Anyway, that's Hopf's argument, is that this function phi, which we called swirling, it's defined on edges, not loops. It doesn't need loops like a lot of the other stuff does, right? Like holonomy and around an arbitrary loop. So we imitated that here. It's all sort of inspired by the classical proof. Thank you very much.